CXK plus DUK. So, our discrete state space model. We can create a residual of this system with, we can rearrange this to give YK minus CXK minus DUK equals 0. And if we find something in the left null space of C, which is W, so we find W such that WC equals 0, then it would be true that W times YK minus CXK minus DUK would become the same as W times YK minus DUK, which should equal 0. We've also defined this matrix M, which has a form D, and then CB, D, CAB, CB, D, all the way down. And if we look at our sliding window, we can then say, in exactly the same, that we have YK minus DUK equals 0. If we choose a different W that is in the left null space of L, so L was C, CA, CA squared, and so on. If we find W that's in the left null space of L, then we can say W times Y minus MU should equal 0 in the absence of false. Then defined some fault vector, P. So P, and I said I'm going to use delta X, delta U, delta Y. I can say that the state update by EP and the output by FP, and because of this P I've chosen here, that means that E must be A, B, and a null matrix, and F must be C, D, I. So if we take our measurements, which maybe we should call Z, yeah, we call measurement Z from now rather than Y. We've got measurement minus MU are our residuals, and pre-multiply by W, then that thing must equal W times NP, when N is like this M, but in terms of the fault matrices E and F. So N equals F, CE, F, CAE, CE, F, and so on. So, difference between the measurement and N times U, pre-multiplied by W, which is the left null space of L, should equal WNP. I then pre-multiply both sides of this by, or essentially pre-multiply both sides by J. So JW times Z minus MU equals J times WNP, which means that thing becomes something called Q. So this thing is a set of residuals. I'll call my structured residuals, I'm going to call them S. S equals QP. P is a fault vector, S are structured residuals, Q is my fault code matrix, and J is a fairly arbitrary matrix that I've chosen in order to make this Q of the form I want. And in order to generate that J, I say JWN equals Q. So JWN equals Q, which means that J equals Q times WN to the minus 1. In general, I can't produce WN to the minus 1, so I use a pseudo inverse. So J is approximately equal to Q times the pseudo inverse of WN, which means that when I calculate this actual J, my real Q is approximately equal to J times omega n, but not exactly because I've used a pseudo inverse. Having created that, S equals QP. If I calculate this S thing, so I take my measurement of the outputs, my inputs, pre-multiplied by the n matrix, that gives me a set of values. Pre-multiplied by W, these values become residuals. Pre-multiplied by J, which I've defined, they become structured residuals. If I generate numbers for those, I can hopefully analyse to work out what my faults were from P using my fault code Q. Okay?
So S is residuals.
Sorry?
Residuals. S.
S are my structured residuals. So W times Z minus W are residuals. These are my structured residuals. So that's the last couple of lectures summarised in one board. What you're going to be doing in your assignment is this. Generating structured residuals from a set of data, analysing them to find what the faults are. Right, your assessment for this module is two parts, one for condition monitoring, one for fault detection and isolation, both equally weighted. You should be spending about equal times on both of them. I'll also warn you now that if you tried it really well in one and think you'll just scrape by the other one or maybe fail at one, that's a really bad strategy. You really do need to work on both of them together, get yourself to pass on both, and then you can always look for improving things after that. Going to be slightly experimental this semester in the timetabling. In that, given that you're all MSc students, you're all numerate, I reckon that possibly you can divide your time up better the weekend. So what Peter and I have decided to do is the first Monday, so next Monday, we have scheduled particular groups for you. So it's basically, right. Peter's schedule, my schedule. Peter will tend to be in in C103A in the mornings and early afternoon. In general, I will be in C141 in the afternoons. On the first Monday, I would like Group A to please make sure you go see Peter in the morning for an hour and a half, and then see me in the early afternoon for an hour and a half. I would like Group B to see Peter in the early afternoon for an hour and a half, and see me in the later afternoon for an hour and a half. The idea of that is so we can make sure we get you all started and running through and you know what you're doing on both assignments. Beyond that, you'll be working full-time, obviously. These are when we'll be in the labs. You can divide your time, come and see which of us you think you need to see at any time. I'm hoping that on the first Friday or about then, we can give you all an informal review of your progress, give you some feedback, make sure you're all not struggling too much. Okay? But basically, I think we're going to leave it to you to decide where you're going to be at various times. The assignment itself for the fault detection and isolation is challenging, but I'm sure you'll be capable of it. It's in the assignment section. I know some of you have looked at it already, and it's, although the data sets may have changed, the assignment is the same as previously. It's a model taken from this Didier paper at the back of the book. The answers to the assignment are not in that paper at all. It's about a different thing. That's about fault-tolerant control. It's interesting, but it's not particularly useful for that assignment. However, the description of a model and the state space matrices come from this paper. So if you have trouble understanding precisely what it all means, the paper might help you to get a handle on it. What essentially I've got is a 3-tank system where we've got 2 inputs, 3 tanks,